Hi everyone, today I brought a very unique question from the chapter Ray Optics. The question says, a short-sighted person means he is suffering from myopia, takes off his glasses and observes a fixed object. The object is fixed through them while moving the glasses away from his eyes. He is surprised to see that at first the object looks smaller and smaller but then becomes larger and larger. If the distance between the eye and the object is 1 meter, for what distance between the lens and his eyes the object will appear smallest? Now before we start solving the problem, first let us understand why does an object sometimes look bigger and smaller even if the size of the object remains same. So let's say I keep an object at some distance from the eye. Okay, this is the lens of the eye and here's the retina. The angle subtended by the object at the eye. This angle determines the apparent size of the object. The apparent size of the object. Meaning, if this angle is large, you will see the object to be big. And if this angle is small, you will see the object to be small. Why? If you take the same object farther, you can see the angle now made by the object at the eye will be small. And you can see even the image here on the retina is small, right? So, though the object size is same, this angle has become smaller, right? This angle theta dash is smaller than theta. So remember, this angle determines the apparent size of the object. The other thing you should be knowing is whenever a function y of x has a maximum or minimum, and at those points dy by dx must be 0. Okay, so this is the concept of maxima and minima. Now let's come back to the original question. They told the person is suffering from short-sightedness, myopia, so he must be using concave lens. So let's the focal length of the concave lens is f0. This is the numerical value and therefore the focal length is minus f0, right? We know that for concave lens the focal length we write minus. Now the object is, let's say, at a distance x from the lens. This is variable because remember he was moving the lens away from him, right? Don't forget the question, okay? The lens was moved away. Now here is your eye and they told the distance between the object and the eye is fixed. So let's say this distance is d and this is fixed. Only the lens was moved. Now when you move the lens, the object distance will change, so image distance will also change. Now we all know for real object the image made by a concave lens is virtual and it is also shorter, right? So let us say this is your image. At what distance is the image? Let's say y. So here is the object, here is the image. I hope you understood how I made this image. Okay, you just have to draw the ray diagram. So here is the object. This ray parallel to principal axis will appear to diverge from focus and the light that passes through optic center will go straight. So these two divergent rays will meet at this point when you extend backwards and therefore this will be your virtual image. So this will be your image of this object, right? So that's how I made this diagram. Okay. Now remember the question was, at what distance between lens and eye will the person see the object to be smallest? Now please understand, when you look from here, you are not actually looking at this, you are looking at this. Why? Because light will first pass through the lens, then it will pass through your eyes, right? So the image made by the lens will be object for your eyes. So in order to see this one smallest, what did we discuss just now? This angle determines whether the size of this will appear big or small. So for the size of this to be smallest, as seen by this person, this angle should be smallest. So we need to find this theta in terms of this x, because once I know this x, I can find this also, isn't it? Because d is given to be 1 meter, right? So we need to find this theta in terms of x, and then we know what to do, because whenever a function has to be smallest, differentiation of the function with respect to the variable should be 0, right? Now to get this angle, I need to find this height. So let me say this is height of the image hi and this is height of the object ho. So to find height of the image, I need to find magnification. And to find magnification, I need to find image distance, right? So let's start with the basic formula. 1 by v minus 1 by u equals 1 by f. Remember, light is coming this way. So if you start from optic center and go opposite to light, you have to take negative. So what is the image distance? Remember, this is the image. So its distance is y. This is the numerical value. While substituting, I have to write minus y. And u is minus x. And focal length is minus f naught. Right? So this is minus 1 by y. Minus minus is plus 1 by x equals to minus 1 by f naught. So take minus 1 by y this side and minus 1 by f naught this side. So you will get 1 by x plus 1 by f naught equals to 1 by y. Remember, y is your image distance. So this will become x f naught x plus f naught equals to 1 by y. So therefore y will be x f naught by x plus f naught. Now for a lens, magnification is equals to v by u, right? And magnification can also be written image height by object height. Remember, we wanted this image height. Finally we got it here, right? V is your minus y and u is minus x. Minus gets cancelled. So hi will be cross multiply ho into y is this, right? So substitute this y here, x f naught by x plus f naught, and here there is one x. That x and this x will cancel. So image height is equal to h naught f naught by x plus f naught. So once we know the image height, we can now find this theta, right? So tan of this theta will be equal to, opposite side is your hi, adjacent side. Well, this much is y and this part must be this total distance which is fixed d minus this x, right? So adjacent side will be from here to here. So y plus this much is d minus x. Now remember, in optics these angles are always considered small. So tan of very small angle is same as angle in radians, right? So tan of angle can be written as angle. Image height, how much we found? h naught f naught by x plus f naught into 1 by this y. Now this y itself has a formula, x f naught x plus f naught plus d minus x. Now this is a wonderful equation because everything here is constant except x, isn't it? Focal length f naught is constant, and this distance between the object and the eye is also constant because the object was fixed, remember. So let's simplify. So in the numerator h naught f naught, here x plus f naught, and now here if you take LCM here, x plus f naught will go up. This will be x f naught plus x plus f naught into d minus x, right? This x plus f naught and x plus f naught will cancel, right? So this will give you theta equal to h naught f naught divided by here x f naught, then x into d plus here minus, so minus x square plus f naught into d plus minus minus f naught x. X f naught and this x f naught also cancel. So your theta will be finally h naught f naught by x d plus f naught d minus x square, right? Now the question was, at what distance between these two this theta will be smallest, right? So for theta to be smallest, the denominator should be largest, right? And if this function is largest, then differentiation of that function should be 0 with respect to the variable. and the variable is x. So differentiation of this function xd plus f naught d minus x square should be 0. Well, differentiation of first term will give you d dx by dx. Second term is constant 0 minus differentiation of x square is 2x. This is d is equals to minus 2x will go that side, so x will be d by 2. Well, this d was given 1 meter, so this will be 1 by 2, 50 centimeter, because 1 by 2 meter is 50 centimeter, right? So this should be 50 centimeter, so therefore this is also 50 centimeter, right?